Welcome to part 4 of the modules on direct lookahead approximations. This is going to be on stochastic lookaheads with discrete actions. So we're going to cover these from two perspectives. One is the use of a very familiar tool called decision trees, and then we're going to extend that to Monte Carlo tree search. So decision trees are an old technique. Probably some of the earliest uses of decision trees were back in the 1950s and 60s. Ron Howard and others were just using this in their courses for MBAs. The first published version of decision trees was by John McGee. He had two articles that appeared in Harvard Business Review in 1964. Howard Rafa's book, Decision Analysis, Introductory Lectures on Choices Under Uncertainty, was in 1968 was sort of viewed as the first big announcement of saying, hey, decision trees are a powerful tool for decision analysis. It's not the first use of decision trees, but it was sort of viewed as the first major introduction. Today, there are no shortage of books in decision analysis, all at some point using decision trees. It's a very powerful technique for a particular class of decision problems. So let's illustrate. I'm going to take a simple asset selling problem. I've got the state of my system is whether I'm holding the asset or not, and I just have to figure out when to sell. Often, people in finance are using this to figure out the value of the asset. The decision is either to hold or sell, and the exogenous information is the price. And we're going to pretend that the price either stays the same with a 50% probability, goes up $1 with probability 0.3, or down $1 with probability 0.2. Now, a decision tree, standard convention, you're going to have square nodes. This is where we make a decision. We're going to have circles. These are called outcome nodes. So when you make a decision, you transition from a decision node to an outcome node. At the outcome node, that's where something random happens. In this case, the price goes up, down, or stays the same. When you're generating the tree, initially we have a asset at $50 we can hold or sell. We can After we make a decision, let's say to hold, now I have an outcome node and I have to see whether or not the price goes up, down, or stays the same. If I sell, then there's nothing and it's just out of the system. Once we've seen the change in price, I'm still holding the asset. And so at this point, we still have a number of other decisions of whether to hold or sell, depending on whether the price went up, down, or stays the same. The way we solve it is we now go backward in time, and this is called rolling back the tree. What we're going to do is we're going to take that last stage where we have the decision. Now, let's say I have some ending value. I've got some numbers out there. For example, at the very top, if I hold, somebody gave me a number of $51.1. I'm going to look at the 51.1 for holding and the 51 for selling, and I'm going to say, well, I'll hold. And if I hold, that value is 51.1, so I'm going to put that value on the decision node. I'm going to do that for each of the other square nodes. I'm going to take the better of the two because that's a decision. I get to choose. Now, the next rollback is the rollback of the random outcome, and I'm going to take an expectation. I'm going to take the weighted average, weighted by the probabilities. So if you have 51.1, and I get that if the price goes up by $1 with probability 0.3, I have 50.10 if I hold, and that's if the price doesn't change, and that occurs with probability 0.5, and the last one is probability 0.3. Take a weighted average of that, and it all comes out to 50.2 if I was holding the original asset. If I sold the original asset, I get 50. This analysis saying I should hold because the expected value in the future is higher. Now, a little bit more interesting example is batters. This is an interesting but fairly artificial example. I'm going to assume I have 3 batters, and I have some history of them. So I have their batting average over a handful of hits, but a very small number of hits. So each one has a very small history. My decision is, do I use batter A, B, or C? And I'd like to make the decision that maximizes the number of hits, not just in that one at bat, but into the future. Now, the exogenous outcome is whether or not the batter gets a hit. So here's my decision tree. I have to choose between batters A, B, and C. Depending on each one, they're either going to get a hit or not. And if they get a hit, we're going to assume they get a hit with the probability given by their batting average. So batter A, he's hitting 360, so he's going to get a hit with a probability of 0.36. Batter B has a batting average of 0.33, and batter C has a batting average of 318. Now, after they get a hit, I have another set of decisions of which of the three batters to use, and then one more time, they may or may not get a hit. Now, what we're going to do is we're going to roll things back and update the batting averages. The thing is, as they get hits, we're going to update the batting average. So, for example, batter A, if we choose him and he gets a hit, his batting average goes from 360 to 366. So we're gonna roll this back. I'm sorry. Batter A's batting average goes up to 366. Batter B's batting average stays at 333 because we didn't use him. Batter C's batting average stays at 318 because he wasn't used. Now, in each of these cases, one of the batters was used in the very first decision. His batting average will change depending on whether he did or did not get a hit, and the other two batters, their batting average stays the same. Now, at this point in the tree, I have a second decision of which batter to use, and I'm going to say, well, I'm going to pick one that has the highest batting average. So at the very top, if you roll back, the best batting average is 366. So I take the best of the batting averages and roll that back. One more time, I have these random outcomes, and I'm going to take, so for batter A, he's going to get a hit with probably 0.36. I'm going to take the weighted average of the two batting averages, and those weighting averages are going to be 0.36 times the outcome of 1 plus 3.66 plus 0.640 times the outcome of 0 plus 356. What we're doing is we're maximizing the number of hits. So with probability 0.36, he gets a hit. In the subsequent at bat, the expected number of hits that this batter will get is 0.366, which is his batting average. If he doesn't get a hit, he gets 0 hits, that's the 0, and his subsequent batting average drops to 356. So now we're going to take 360, the probability he gets a hit, plus 0.64 times 0 plus 356, and it all comes up to 720. That 720 is the expected number of hits over this and the subsequent at bat. Same thing for the other players. Now at this point, we see which batter is the batter that we would most like to use. It turns out to be batter B. Batter B doesn't have the highest batting average. Turns out he's also a player with very few at bats. And so in effect, what we're doing is we're being rewarded by the value of learning, that if we put batter B up and we see whether or not he gets a hit, there's a higher likelihood that he could get a hit. And if he does get, I mean, he's got the 333 batting average that he gets a hit, but if he does get a hit, that pushes his batting average up much higher. Okay, that was very simple. And generally, people are using decision trees for problems with relatively simple decisions. In practice, the uncertainties tend to be much more complicated than this little illustration. But the decisions, and often people are using decision trees when it's just a single decision. Should I purchase or sell this company? Should I launch a product? It's just a single decision, but with very complex uncertainties. But there are many applications where you'd like to use decision trees, and but they explode. This is this image. I've used it before. Very simple image of buy, sell, or hold an asset, and you see how quickly it explodes as we move into the future. There's a lot of problems that have not only more decisions, but they have many more outcomes. And so as you roll forward, the decision tree will just explode. So computer scientists have developed a powerful technique they call Monte Carlo tree search, where they say, okay, I want to use a tree. I want to look forward. I don't want to enumerate the tree. So what they're going to do is they're going to grow the tree in an approximate way. And there's 4 steps called selection, expansion, simulation, and backpropagation. Uh, in the selection stage, so let's imagine I have a partial tree, and what I have to do is select which action that I'm going to expand. So I have to, pick some node that I'm going to work on. The expansion phase says, what action might I take? And after that action, I'm going to investigate future outcomes. In simulation, let's say I reach out to a node in the expansion phase that I've never visited before. We're going to use a simple idea of a rollout policy. Now, the rollout policy is a policy within the policy. So we're doing a direct look-ahead policy. We're going to approximate the tree using Monte Carlo tree search. Within Monte Carlo tree search, there are going to be places where I say, I don't know the value of being in this state. Do you have some simple policy that will allow me to do a rough approximation? That's called the rollout policy, and they just assume that you have one, something simple. Now, the 4th step is backpropagation, where as you do this peek ahead, you then propagate this information back. And this is all done through an equation where we're going to see almost all the policy, we are going to see all the policies at work, one of which is a value function. So as we're reaching out at every node in this tree, the way I'm looking out is I'm going to have an immediate cost or contribution, let's call it a contribution. Then I use a downstream value that captures the future. Now, I've been approximating the future sometimes with the rollout policy, but sometimes with the benefit that maybe I'm up in the 2nd or 3rd level of this, and I have the benefit of decisions further into the future. Now, that last term, the one with the square root, this is called upper confidence bounding on trees, UCT. And what it is a bonus that encourages exploration. And within there, so I'm at a node in the tree. That's a state. It's been visited a certain number of times. I take the log of that. I divide it by the number of times I've not only visited the state, but also have taken that action, which is going to be smaller. Now, this logic encourages exploration. So the thing that the computer scientists have proven is that if you run MCTS an infinite number of times, that numerator is going to grow, but it's not going to grow as quickly as the denominator, which means that whole term will eventually go to 0. But in the beginning, it's going to be a larger term, and I can control how big it is through that theta UCT parameter. Okay, so that's a tunable parameter that we have within our policy. So this is a policy within the policy. I'm doing a look-ahead policy, direct look-ahead policy, but within the direct look-ahead policy, I have a policy at node S tilde where I'm going to choose action A tilde by optimizing this term, which has both a value function and a heuristic bonus term. So notice that this policy, we have a PFA, that's the rollout. We have a CFA, that's the bonus term. We have a VFA, and everything rolled together is a form of DLA. Okay, so we're just sort of throwing everything in there. So when people say, oh, they've solved the game of chess or Go, because this is the logic, this is the core logic inside the successes with games like chess and Go. It's a look ahead. But the lookahead uses all 4 classes of policies. So when people say they use reinforcement learning, this is where I say, okay, I don't actually know what that means because it's all 4 classes of policies. If you go to section 19.8 of my advanced book, I talk about 2 forms of MCTS. The classical form with the rollout policy, I refer to that as pessimistic MCTS because the rollout policy is ad hoc and heuristic, and it gives me a lower bound on the value of being a node. Now, what you can do is you can do a rollout, then act as if you know everything that's going to happen in the future, and then put that into a math programming algorithm and solve it optimally. So that's going to be an optimistic estimate because I'm allowing myself to see into the future. Now, one warning, solving that look ahead optimally is expensive. You get much faster convergence, but a lot longer CPU time per iteration. So it's hard to say how well this is going to work depending on applications. Typical application of MCTS creates a tree like this. So instead of that explosion that I illustrated before, what you're doing is you're exploring different parts of the tree to different depths. So off to the right, you see that we're really exploring it deeper because the logic says, hey, wow, this looks much more promising, whereas we've pruned actions in other parts of the tree. Now, all of this is being called at a point in time. It's a look ahead. So if I'm at time t, I call my MCTS, we do all this planning in the future, and then we roll forward and do it again. And then we roll forward and do it again, and so on. So this is a direct look ahead. One of the things nice about MCTS, it's immune to large state spaces. Okay, so whereas vanilla dynamic programming, it can't handle vectored value state spaces, can't handle continuous state spaces. MCTS is immune to all that. I can handle high dimensional states, I can handle continuous states, which also means that it's very powerful when you're updating beliefs. Okay, now the literature on MCTS seems to ignore the fact that it's not solving a problem, it's a policy. However, there is an extensive literature in computer science where they use it as a policy. And what they'll do is they'll play games, and this is how they ended up with the breakthroughs in chess and computer Go. Okay. Once again, more on policies on the website. Just look under direct look ahead approximations.